So this lesson is about the optical refracting telescope. Now, by definition, it's an optical instrument designed to produce an angular magnification for a very distant object. Now, before we proceed, I'm just going to review this idea of angular magnification. So let's say you're looking at an object in the distance over here. The angle subtended to would be the angle that's made with the horizontal. Now, for very long distances, then the angle is no longer tan of the angle, but it can be simplified to be just the angle. Now, this is the angle subtended to. So what we're looking for in an optical refracting telescope is something that will create or generate an angle to an image which will be much bigger. Okay, so that's what our angular magnification will be. It will be an angle which is much greater to an image. So say you're looking at a picture of the moon. The actual moon to you would make a tiny angle because the moon is so far away. But the virtual image that is made by the telescope would be much, much bigger and would create a much bigger angle there. Okay, so this is just a little bit of review. We will come back to this in some more mathematical questions. Now, the ray diagram is very strange, so it's not one that you would necessarily construct. You're more likely to have to just learn it off by heart. So let me explain the peculiarities of this ray diagram. The first one is that the rays come from a very, very far away object. And so, to simplify, you say that the incoming rays are parallel, as if they were coming from infinity. Now, the rules are still pretty much the same, but there is an issue. With rays coming from infinity, what we're saying is that your U value is equal to infinity. This has the peculiarity of making the image distance V equal to the focal length. Now, why could that be? Have a think about your lens equation for a second. Now, hopefully you thought this through. If the 1 over the focus length equals 1 over infinity, which is the object length, then 1 over infinity equals 0, and what we're left with is that the object distance is equal to the focal length. Now, what that means is that the image is focused on the focal point. So that is really impossible to draw. Okay, so this would be tiny and it would be...
Apple.
Thank you, Leia. So that would be tiny and it wouldn't go... you wouldn't actually be able to draw it. So this is the way it's represented on a diagram, and you're just going to have to learn that. Okay, so the lines converge on the focus, but actually to show the height of the object. Now, what are our construction rays to do this? Well, the center construction ray continues the same way, straight through the center. Okay, so the best way to draw the image would be to just draw this one construction ray and then join it with the object height at the focus point there. Now, once you have that, you can draw the other two rays. So I'm going to try a very hammy attempt to try that there. So let's say if you have your construction ray coming in like that, and your focus point is here, well, that would be where to draw the object. So your first step would be to draw the construction ray down through the center and straight, and then your image would be here. Let me tidy that up a bit. And then knowing that that's the point where they meet, you can then show the other construction rays, because these are parallel lines. So what happens here at the lens is there is refraction and they join, and then this one is parallel. Oops. And at the lens, it would bend to join this point, like that. It's actually impossible to use a ruler with this program. Okay, so here we go. So that would be your height. And the next really interesting thing which makes this work is that the focal point for this first objective lens is actually also the focal point for the eyepiece lens. So we'll talk about that next. Okay. So what now happens at this second lens? Well, the image from the first objective lens has focused onto the focal point of both lenses. So now here we get a magnified image which is focused at infinity. Okay, now why? If you remember the rule, if the focal length equals the final, then you end up with a focused image at infinity. And that's your second.
Yo no estoy tocando nada.
Very good, thank you. So that's your second lens image, because all you have to do to find that image would be to do your construction ray through the center here, and then your ray which focuses at this point. Okay, thank you. Okay, so let me just run through that again. Your construction ray through the center is pretty much the fixed, reliable one. Okay, where that hits the top of the object's projection, the image here, that is your point to then fill in one of those other construction rays. This is not a very common diagram to have to construct, but just remember that the one consistent construction ray is the central one through here and through here. Your final image is an inverted virtual image, which is used for looking at very far away astronomical objects. So now we're going to define the equation for magnification. This is the final equation that we're looking at. The magnification is the ratio of the focal lengths, the focal length of the objective over the focal length of the eyepiece. That will give you your angular magnification. And first, let's have a look at y. Now we need to look at the ratios of the angle subtended to. Now, if we remember the original formula for magnification, or angular magnification, is the angle subtended by the image over the angle subtended to by the object. Let's have a look at the object first. Now, the object is infinitely far away, somewhere, which is not infinitely far away, but very, very far away in the distance. And the rays, if you can imagine, if instead of arriving at an objective lens, they arrived at an eye, like this, you can see why the angle at which they arrive at is this one. Now that angle, which is from the eye to the infinitely far away object, is also equal to this angle. Can you see that? And if that's the case, then we can find the angle subtended to by using h1, the height of the image, over or divided by the focal length of the objective. Now you should be able to see that that's because this is a nice triangle here. Okay, so we're using the ratio of these two distances to find the angle there. Again, remember that assumption. Tan of the angle equals the angle for large distances, and f0 is assumed to be much larger than h1. Okay, so that gives us our, down here, that gives us our ratio here, our angle subtended to by the object. Now let's have a look at the angle subtended to by the actual image that you see, which is all the way down here. Okay, so we get this enormous image all the way over here. And what is the angle subtended to? Well, here is the eye. The eye is looking down at the object in that direction, and the angle can be seen as represented by this triangle here. Now this triangle, again, can be worked out, but this time using the height of the object, the height of the image over the focal length of the eyepiece lens. Now remember, this is the same image which just happens to be focused at the same point where the two focal lengths meet. Now if we substitute those two in, our height of the image over the focal length for the objective for the object angle, and the height of the image over the focal length of the eyepiece lens for our angle of the image, then what we get is common terms that we can cancel out, and then these flip over, so we end up with the focal length of the objective over the focal length of the eyepiece. And that would give you the angular magnification. So now try this question. In the setup below, the focal lengths of both lenses are equal. State the angular magnification using the angle shown below, and use the diagram to derive an expression for the magnification in terms of the focal lengths. So do you remember the derivation that you've just gone through, and can you do it on your own? Off you go and try it now. If you were stuck and you couldn't do it, you need to replay the previous slide and work through that derivation again. Hopefully you did do it correctly, so you can go on to the next question. Let's look at some advantages and disadvantages of using big lenses. So the quality and diameter of the objective lens, that's the first lens, the one that receives the light, is a very important factor in considering quality of image. The larger objective has two advantages. Note this, something you have to learn off by heart because it will come up. By being larger, it will collect more light, so it produces a brighter image. Okay. The second one is to do with diffraction. Because it's larger, there'll be less diffraction, and because of that, you would have better resolution of images. However, and this is where you get the marks, larger objectives have aberration problems, both spherical and chromatic, and these reduce the quality of the image. Now these questions pose quite a challenge, so if you're not feeling confident yet, I suggest that you fast forward the video to the next series of questions, because they're a little bit more straightforward. So stop now if you want to do some easy practice, and go on to the next slide if necessary, or the next a couple of minutes away. However, if you want to try something challenging straight away, we're going to carry on with these questions now. So a student hopes to construct an astronomical refracting telescope that produces an angular magnification of at least 100. If she chooses an objective lens of focal length 68, What is the minimum power? Well, you know power equals 1 over the focal length. So it will be 1 over 0.68. Remember, power diopters are in meters. And that should give you 150 D. (43) Venus has a diameter of about 12,000 kilometers. What angle does it subtend at the eye when it's at a distance of 2 times 10 to the 8 kilometers? So that would just be your object distance divided by the distance to the eye, which should give you 6 times 10 to the minus 5 radians. B. A refracting telescope with an objective lens of focal length 120 centimeters is used to observe Venus. What is the diameter of the image formed by this lens? By this lens being the first objective lens. Now for this, you need to remind yourself of that derivation you did a few minutes ago. So here is our image formed by the objective lens, and the angle subtended to we've already worked out, because as you know, it's the same as the angle subtended to by the eye of the object. So your answer to A is your angle here, which happens to be the focal length of the objective. So the height of the image divided by the focal length of the objective lens will give you that first angle that you worked out in A. Okay, so you should be able to use these two pieces of information to find H1. Now for part C, an eyepiece lens of focal length 1.5 is used to form a final virtual image at infinity. So then that goes through here and it's focused at infinity. So what actually you're trying to find out is this angle here, which you should remember is now equal to the height of the image divided by the focal length of the eyepiece, H1 over Fe, which are given in the question. Focal length is 1.5 centimeters, and your height of the object you found in part B. Now for D, use your answers to A and C to confirm the overall angular magnification. Well, it's just a ratio of the focal length, so just use your values of focal length to find that. Okay, so question 44. The refracting telescope consists of lenses of focal length 86 and 2.1. Okay, so this is going to be a bit of a memory question, but the eyepiece lens is the one that has the smallest. The best way to remember it is that it's the opposite of the microscope. With the microscope, it's easy to understand why the eyepiece lens would have a large focal length. And here it's a little bit more abstract, so you just have to flip it round. Okay, so the eyepiece has the smallest. Calculate the angular magnification in normal adjustment. So that's easy. That's just applying the formula, F0 over Fe. Now, if the objective lens was replaced with another one having twice the diameter, so that's a simple definition question. If you have twice the diameter, then you are going to have a much brighter, better image, but you're going to have huge aberration effects. Here's some more questions, and they are a little bit easier. An astronomical telescope has an objective focal length of 900 millimeters and an eyepiece of focal length 18. Okay, so here's your objective and your eyepiece. Assuming the instrument is in normal adjustment, by that it means assuming that it's focused and it's working. Calculate the separation of the lenses Now, for this question, you have to remember that the focal lengths meet. So the focal length of the objective meets at the focal length of the eyepiece. So the total distance would be the addition of both focal lengths. The magnifying power achieved, B, would be simply a ratio of f0 over fe. So that's a straightforward question. And you should get 918 for the first question and magnification of 50 for the second. The angular magnification in an astronomical telescope in normal adjustment is 4. If the distance between the lenses is 6.25, calculate the focal length of the eyepiece and the objective lens. Okay, so to do this question, you're going to have to come up with two formulas. We know that the distance between the lenses is the addition of the both focal lengths. So focal length of the objective plus focal length of the eyepiece be equal to 625. And then we also know that the magnification, which is 4, is equal to the ratio of the focal lengths. So f0 over fe. So what you have is a simultaneous equation which you can use either to solve. Okay, and you should end up with a value of 125 for one and 500 for the second. Number 5, an astronomical telescope in normal adjustment has an objective lens of focal length 20 and a separation of lenses of 25. The telescope views a distant object which subtends at an angle of 5 times 10 to the 2 at the objective lens. Calculate the angle subtended by the final image. So if we have our lens diagram here and your image here, well, our final image, remember, ends up somewhere over at infinity, but we use this as a place to find the angle, because as you remember from what you derived, your angle subtended to by the object can be seen, and your angle subtended by the image can be seen here. And this height of the image projected by the first objective lens is common to both. Now your focal lengths are as follows. The objective length focus is 20 and your eyepiece lens must be 5 because remember they add up to 25. So this whole distance is 25. So the best way to do this is if you know that your angle subtended to by the object is 5 times 10 to the minus 2. You use that to find, to find h1, because h1 over 20, actually 0.20 would give you that. So that will give you the height of the image, and if you know the height of the image, you would divide it by the focal length of the eyepiece to give you the angle subtended to by the image. Question 6. An astronomical telescope in normal adjustment has an objective of focal length 0.9 and lenses are separated by a distance of 1 meter. This means that your eyepiece focal length is 0.10 meters. When used to view the full moon, the image subtends an angle of 51 times 10 to the minus 3 radians at the eyepiece lens. If the distance between the Earth and the Moon is 3.8 times 10 to the 5, calculate the diameter of the Moon. So what that's saying is that if this image here is subtending to an angle of 51 times 10 to the minus 3 to your eye, then the actual real image, which is at infinity, well, not infinity, but actually 3.8 times 10 to the 5 kilometers, then the actual size of that object subtended or divided by the distance to the eye should give you the same angle, right? So HI, this one, this height, divided by this distance, which is the focal length of the eyepiece, should be equal to the actual height that you see of the Moon divided by the distance to the Moon. Okay, so you can use that to find the diameter of the Moon, which is this. Now this is a question from last year's paper 3. An astronomical telescope is used in normal adjustment. The separation of the lenses in the telescope was 0.84. The objective lens had a focal length of 0.82. What is the magnification of the telescope? Yes, it's that easy. It's the ratio of the focal lengths. Focal length of the objective over the focal length of the eyepiece. B. Outline why sign conventions are necessary in optics. Well, we use sign conventions to tell if it's a lens which is converging or diverging. And we also use it to say if the image is real or virtual. Part C. A student decides to reverse the positions of the same lenses without changing the separation to form an optical microscope. So you go from telescope to microscope. The student's near point is 0.25 meters from her eye. Show using a calculation that the image formed by the objective lens is about 0.19 meters from the eyepiece. Now what's horrible about this question is they've swapped it round. Now what they're saying is that this objective lens, this one here, is now treated as an eyepiece lens. Now what that means is that your new eyepiece lens, which has a focal length of 0.82, now makes an image here. So that V distance is at the near point. So we have F, which is equal to 0.82, and we have V, which is 25 centimeters. So if we use our lens formula for that, we have 1 over 0.82 equals 1 over U, which we're trying to find, minus 1 over V, which is 25. Now it's minus because it's a virtual image, and you should get your value 0.19. So now the next part, calculate the distance between the objective lens of the microscope. The objective lens of the microscope, which is now the other lens. They're trying to trick you by changing the name of everything. So we've done the eyepiece, and now we're going to look at the other one. So where was the object? Where was it before? Now we know that the focal length this time, which is going to be in there, is 0.02. And the object will end up at a distance of 0.19 from the eyepiece. So we can easily work out using the formula exactly the same as before. You have 1 over 0.02 equals 1 over u, which is what we're looking for, plus 1 84 minus 0.19. Because remember, this distance here is 84 centimeters, and this is 19 centimeters. But we're actually interested in this distance here. Okay, so which is 0.84 minus 0.19. Okay, determining the overall magnification of the microscope is just using the formula for magnification, which is equal to V over U times D over F plus 1. So you substitute your values in to get your magnification.